Now that we've learned how to do hypothesis testing, there's still a few additional analyses that we need to learn to conduct to supplement the results of our statistical decision. So if you remember from our previous lectures, we were looking at Applebee's employees and implementing a new training that we sampled with recent hires, and we compared them to the performance of all employees with the old training. And we ended up coming up with the decision to fail to reject the null hypothesis. In other words, we found that there was no difference between the two. And so there's additional analyses that we can conduct that will help us make a better decision on whether or not we will implement this new training program. Those additional analyses include the effect size, the confidence interval, and we should probably take a few minutes and talk about statistical power. So let's go ahead and let's begin with the effect size. Now you may have noticed that when we went through the steps for the 7 steps for hypothesis testing, that there were several points in there that we made fairly subjective decisions as researchers. So for instance, we talked about how the researcher decides what alpha is. And so if the researcher is deciding what alpha is, then that alpha cutoff or our type 1 error rate is fairly subjective. Additionally, we talked about how the z-statistic is influenced by the sample size. In general, the larger the sample, the higher our z-statistic is going to be, and so the easier it is for us to reject the null hypothesis. So given these two fairly subjective components of hypothesis testing, it's possible that our statistical significance, or our decision of whether or not to reject or fail to reject the null, may not be that meaningful. So in addition to our hypothesis test, we also want to calculate an effect size. So based on the scenario we had a two-tailed hypothesis test with an alpha of 0.05. And so here is our normal distribution. We have our cutoffs, our critical values at an alpha of 0.025 in each tail. So if you add those together, you get an overall alpha of 0.05. And the corresponding z-critical for this cutoff point is 1.96 and negative 1.96. And so if you remember, at an alpha of 0.05, we failed to reject the null hypothesis. We concluded that there was no difference between the new training and the old training because the z-statistic that we calculated was 1.83. It did not exceed our critical value of 1.96. And that was in the positive direction because our sample mean had a higher performance level than the overall population mean with the old training. However, if we had set our alpha to be 0.10, our overall alpha at 0.10, a 10% chance for a type 1 error, then with our two-tailed test, we would create two critical regions in the extreme portions of our distribution that accounts for 5% of the population. And so our corresponding critical values for z would be negative 1.65 and 1.65. So if our z-statistic that we calculate with the sample that we collect exceeds that critical value of negative or positive 1.65, then we will reject the null hypothesis. Now, assuming everything in our calculation stays the same, our z-statistic would still be 1.83. And so as you can see on the slide, that blue vertical line shows us that that z of 1.83 falls within our critical region. So that tells us that our sample mean of 76 when compared to the population mean of 72, given the measure of standard error, occurred at a greater than chance level when we set chance at a type 1 error rate of 10%. So ultimately what we see is that the alpha that the researcher decides on may have an impact on the statistical decision. So before an alpha of 0.05, we failed to reject the null hypothesis. We concluded that the new and the old training were no different from each other. However, if we increase that alpha to 0.10, our statistical decision now is to reject the null hypothesis. It appears that the new training resulted in higher performance than the old training. The hypothesis test results are not only affected by the alphas that are set by the researcher, but it's also affected by the sample size that the researcher selects for the study. So if we want to demonstrate how the sample size affects our z-statistic, then we have to look at the formula itself. And so we'll start with the standard error. So if you remember, from Thursday we talked about the standard error being the standard deviation in the population divided by the square root of n. And so if you look at the formula, you see that the standard error is a function of the sample size. Because n is in the denominator, the larger n is, the smaller standard error will become. So based on our Applebee's scenario, we said that the standard deviation in the population with that old training was 12. We then sampled 30 employees and gave them the new training, and so that's our sample size is 30 employees, and so that goes in our denominator. So we'll take 12, we'll divide by the square root of 30, and if you recall from last week, the standard error we got was 2.19. So if we put that into our z-statistic, we see that the z-statistic is affected by the standard error. Standard error is in the denominator again, and so because it's in the denominator, then the smaller the standard error is, the larger the z-statistic is. So based on the numbers that we presented in our scenario, we had our mean with the new training with a performance appraisal rating of 76. The mean of the population with the old training was 72. And our calculated standard error was 2.19. So the resulting z-statistic is 1.83. And we see that in this slide as that blue vertical line that represents our z-statistic. Now we see that it does not exceed our critical value of 1.96, so it does not fall in our critical region, and so we failed to reject the null hypothesis. We would say that there's no difference in performance between the new and the old training because it occurs at a greater chance than we're willing to accept for a type 1 error rate. So greater than 5%, or a probability of 0.05. So what if instead of sampling 30 employees and giving them the new training, instead we sampled 1,000 employees? So our standard error formula would still be the same, however our numbers would be slightly different. So our standard deviation of the population is still 12. However, now we're dividing by the square root of 1,000, or the 1,000 employees that received the new training. And so when we run the calculation, we end up with a standard error of 0.38. And so notice that this is quite a bit different than the standard error that we had before. Before it was 2.19, and now we've reduced it down to 0.38. Again, here is our z-statistic formula, and as we mentioned before, that if we're looking at our standard error, because it's in the denominator, the smaller our standard error is, the larger our z-statistic is going to be. So if we plug in those values again, our mean of 76 for the sample, minus our mean of the population of 72, but now we're going to divide by 0.38. So when we do the calculations, we see that our z-statistic is now 10.53. That is drastically higher than it was before when we only sampled 30 employees. And in fact, our statistical decision has changed. So before, we failed to reject the null hypothesis. We said that there was no difference between the new and the old training programs. But now, if we had sampled 1,000 employees and gave them that new training program, assuming the mean stays the same for that sample, our z-statistic would increase to 10.53. It would fall within our critical region, and we would reject the null hypothesis. In other words, we would say that there is a difference between the new and the old training programs. In particular, we could say that the new training program results in higher performance than the old training program. And that's because we had a larger sample size. So if our statistical result, our statistical decision, is affected by subjective components such as the alphas and the sample size, which are both under the control of the researcher, then we need another measure, a less biased measure. And that measure is going to be the effect size. As you might expect, the effect size is not affected by alphas nor sample sizes. Because it's not affected by the sample size, the effect size is based in a population distribution of scores. And so when we say a distribution of scores, what we're talking about is that the distribution is made up of individual employees. So no longer groups, no longer samples, no longer means of groups, but rather the individual scores for each one of the employees' performance level. So if we look at our formula, we have the symbol D, that stands for Cohen's d, and in our formula we will take the mean of our sample, we will subtract the mean in the population, and then divide by the standard deviation. And so again, note, we're using standard deviation now, we're not using standard error. And so that tells us a result at the individual level rather than the group level. You will also notice that with the formula that it's not much different than our z-statistic formula. The only thing that has changed is that denominator. It is no longer standard error, it is now standard deviation. But we'll call this the effect size. We'll call this D, which is the symbol for Cohen's d, or Cohen's effect size. If we plug in the numbers from our scenario, so we put our mean of our sample of 76, we subtract the performance rating mean of the population, it's 72, and we divide by 12, then we'll get our effect size. So remember, 12 was our standard deviation. We end up with an effect size of 0.33. Of course, that's just a number, so what does 0.33 represent? Well, in this case, 0.33 is the effect size, and it represents the shift in the population distribution of scores. And so you'll notice on the screen here that we have two population distribution of scores. We have one for the current training program, or the old training program, that's in blue, and then another for the new training program, that is in red. And so the effect size gives us a difference between the new and the training program, not in raw scores, not in performance ratings, but rather in terms of variability, in this case in standard deviations. So we're saying there's a shift with this new training, a population shift of 1/3 of a standard deviation. If we were to write this out, which you'll be asked to do on worksheets and on the exam, then we would say that we can expect on average that any individual Applebee's employees, and remember it's the individual employee because it's on a distribution of scores, so any individual Applebee's employee's performance will increase with the new training by 0.33 of a standard deviation over the old training program. We would call this a small effect. Now we'll come back to categorizing our effect sizes as small, medium, and large in a minute. But first I just want to make sure that we understand what is included in our explanation of an effect size. So when explaining an effect size, there are 6 things that you need to include in your statement. You need to specify that it's at the individual level. So with a hypothesis test, the hypothesis test results, whether we reject or fail to reject the null hypothesis, is at the group level. The effect size, however, is at the individual level. So we also want to identify who or what is being measured. So in this case, we're talking about Applebee's employees. We also want to identify the measurement that is being used. In this case, we are measuring performance. We also want to identify our populations, or the groups, so in this case, the new and the old training programs. We would like to include the difference in terms of the standard deviations, so that number you calculate. The standard deviation should represent the shift, so you should talk about that standard deviation as saying that one group is higher than the other group, or one group is lower than the other group in terms of that standard deviation. Then finally, include the size of the effect. Is it small? Is it medium? Or is it large? To determine whether effect sizes are small, medium, or large, Cohen gave us some conventions for us to follow. In other words, some rules of thumb of how to categorize effect sizes. So if our effect size is around 0.2, we'll say that it is small. If it's around 0.5, we'll say it's medium. And if it's around 0.8, we'll say it's large. And so whether it's small, medium, or large will depend a lot on the context itself, but in the behavioral sciences, we tend to use these particular 3 rules of thumb to categorize effect sizes. So when you're looking at your effect size, calculate the category that is closest to your effect size. So they're not cutoffs. Go with the one that is closest to. So in this case, if we had 0.33, well, 0.33 is closer to 0.2 than it is to 0.5. And so we would say that this is a small effect. But what's most important is that our effect size now allows us to make meaningful predictions. And so this is something that we won't do in this class, but if you were to continue in statistics, we can then go on and do something that's called utility analysis. We can take our effect size and estimate the amount of savings an organization might have given a particular intervention. Or if it has to do with behaviors, we can get an estimate of how behaviors would change for a particular group based on the individual effect sizes. So in conclusion, the effect size gives us a less biased estimate of the differences between our 2 populations. So it provides additional information that can help us make decisions. However, they don't replace the hypothesis test results. So we don't have a preference for the effect size over the hypothesis test, nor the hypothesis test over the effect size. There are 2 different measures that provide us with additional information that helps us make informed decisions. So we always want to consider both rather than just one or the other. We happen to like the probability aspect of hypothesis testing, and we also like the fact that effect size are not affected by alphas or by the sample size.